So we are going to study that how we are going to define the model and the experiment description, right? So we built a model and now we want to test the model. So we need to do some experiment with it, right? And in that experiment, we need to make sure that how do we describe the model, how it was working in each context, like there was 2 and 3 and 4 outcomes, and then we need to also describe the outcomes. So these are the ways to describe your model as well as the experiment you perform with it. You can use mathematical formulations. The other expressions, like you can use differential equations, they are used to model continuous systems where changes occur smoothly, like fluid flow population dynamics. And you could have how a state variable x changes over time. You have dx, basically derivative of x, d of t equals fx of t, fraction of d of x dt fx of t. This is basically the function for calculating the derivative of x, or in the words, like I told you that the derivative or this small delta shows a small change which occurs in some variable. Then we can use algebraic equations where are used in static models where the relationship between variables don't change, like y is equals to mx plus b. These are like when we have simple lines systems we need to look forward to. Okay. Stochastic equations can use randomness and they use probability distributions. You can use you may know some of them like normal, binomial, Poisson, or I think there was more like binomial, and there was something called I can gamma, beta. These were all the distributions. I can just recall a little bit of them right now, but you can use them to create a model, right? So represents a random disturbance. I don't get what's written, but I just get the idea, right? You can either use the mathematical formulations, you can use graphic representations to represent your model. Always remember what we're trying to do and the experiment we're done with it, right? We can use block diagrams. They use to present systems as blocks with inputs and outputs showing the flow of information or materials through the system. Okay, this is especially useful in control systems or process modeling, right? So especially block diagrams are useful when you're trying to model the computer processes. You can use flowcharts, they visually represent sequence, and they are commonly used for discrete event models and process simulations. So we talked about the block diagrams are used for process modeling or control systems, like where you have some control and where you like electric circuit where you can turn on or you can turn off. You can use flowcharts to represent the discrete events and process simulations, state diagrams that tell you they represent the various states and the transitions between them, and they also do it between discrete like finite state machines. Network diagrams, they for systems with interconnected components, electrical circuits, transportation systems, social networks, they provide a visual representation of the nodes, right? So you can graphically represent your data. Yeah, finite state machines, they are basically for data organization, computer organization design, data architecture thing. But yeah, it's that these are machines that we kind of design to understand the lower level details of computers. That's the easy way to say it. Natural language descriptions, you can use system description. Like natural language is often used to provide a qualitative description of the model or the experiment. System descriptions, a narrative explanation of system components, processes, and interactions, like this. This model simulates the flow of traffic through a network of roads where each intersection is modeled as a node and the rows between them are represented by edges. Then we can make some assumptions during the system descriptions that we assume that all vehicles travel at a constant speed and that no traffic lights are present, right? So we kind of use descriptive language to describe the models if we don't want to use any visual representation. Then we can get the, we can write the assumptions that we have, right? They are essential for communicating the model to a broader audience, including the stakeholders who do not have a technical background, and they're kind of useful in the modeling and the documentation later on. Okay, so we are in the simulation languages and software tools. Of course, in this technical area, we shouldn't be doing all this work ourselves, so there are tools here. We have some modeling languages. We have Simulink, a graphical modeling language used for dynamic system modeling. We have Modelica, an object-oriented language for component-based modeling of complex physical systems. We have PatriNet, a mathematical modeling language often used for describing distributed systems and discrete event simulations. So there are like Simulink, Modelica, and PatriNet. Simulink, Modelica, and PatriNet. And then there's a software for simulation. We have MATLAB or Simulink. They provide a platform for building and simulating dynamic system using block diagrams. Sorry. And then we have AnyLogic, allows for multi-method modeling, discrete event, agent-based, and system dynamics. And we have basically Arena, a discrete event simulation tool used for process modeling, right? It's a discrete event simulation tool. The tools really help to simulate easily. And then experimental design and protocols. In describing experiments conducted with models, it's important to outline the experimental design and protocols used. So these are the essential things to really, write when you're really working with the models. Define the starting values of the model variables. For example, in a traffic model, the initial condition could be the number of cars on each road at the start of simulation. So you need to give some initial conditions. Control parameters specify the value of parameters that remain constant during the experiment. Gravity is a physical simulation. Or sometimes you also want to maybe change the velocity or temperature or whatever. Variables and outputs. For example, this is an important example. So for example, when we do some experiment in jar, like we made some model of chemistry, and they, put the cover on, then the temperature is going to be the constant over all the experiment. So that could be a control parameter. Variables and outputs identify the key variables. In a biological population model, the output could be the population size over time.